Howdy class, Mr. Warner here. We're going to do a little learning about single displacement and double displacement reactions and maybe a little combustion. So I'm not there in class, but I've got this video here for you to go through the lesson with me, and hopefully this helps out as you're going through these examples. You've looked at these types of reactions before, but now we're going to get into some little specifics and little tricks because sometimes these reactions don't work as we think they should. So if you remember a single displacement reaction, you would have a compound reacting with an element, and it would create a new compound and a different element would form, right? So this example uses copper 2 chloride and zinc, and when we're done, it produces zinc chloride and copper. So when we talk about like the general layout of these reactions, we look at this idea of A plus B. So there's your compound. And then your element is C, and you'll notice that things will switch places. Now, it depends on what it's looking at. So in this case, if this is a metal, I'm writing on a new tablet, so I'm just not used to this one. And then B is your nonmetal, right? The way this is written is C would be a nonmetal as well. Okay, so that's why B and C have switched places. The other way you can see it is like A, B plus D produces D, B, and A. So in this case, your D element is a metal in this case. So we've got our metal, and it replaced our metal element. So it kicked out the other metal, right? That's essentially what's happening in your single displacement. So there's the metal is A, right? So you can have a metal replacing a metal, or you can have a non-metal replacing a non-metal. Either of these forms work. It's just a matter of watching which element is involved. Hopefully you like my hat. I just thought it'd be fun to wear it as I'm here. So for single displacement reactions, to know whether a reaction is going to work, because in grade 10 we just said, like, if you can recognize element plus compound produces new element and a new compound, that was all good. But what you're going to realize is that some of these reactions don't work. And in order to predict which ones would actually work, we use something called the activity series. So on the back of your periodic table, you'll see an activity series of metals, and you'll also see one for nonmetals. Here's a sample of one for metals. And so the way this works is, I'm just going to move this over, is that the metal that is higher on the list is able to displace something else that's in a compound. So if I have potassium is very reactive. It doesn't want to exist by itself. It would rather exist in a compound. So if we put it into a reaction in its elemental form, it doesn't want to stay that way. So if the compound contains something like iron, right, then because potassium is more reactive, it can kick iron out of the compound, and that reaction would work. So what we see is if the element is higher on this list, it will displace the metal that's in the compound to form that new compound. If the element, the metal is higher on the list, is already in a compound, then nothing happens. No reaction will occur because it's already in its stable form when it's a compound. So there's a lot going on with this, but you'll also see hydrogen is in there because hydrogen sometimes behaves like metals do, right, with regards to how it reacts. And you'll often see, sometimes we talk about like water or acids being involved, so that's where hydrogen would come into play. So we're going to try this and try a few examples to figure out what reactions might actually work and which ones won't. So we're going to use the activity series. I'm just going to keep popping my little head over. So if we've got the activity series, I've got a set up here on the side. I'm just going to sort of shrink this a bit so we can see it all, hopefully. Bear with me. All right, so here's an activity series on the side. Potassium's at the top, most reactive. Then we got sodium, lithium, and so on, all the way down to gold at the bottom of that list. So we're going to try and use this activity series to predict what's going to happen. So we have iron, right, Fe, and we have copper 2 sulfate. So we need to compare the metal copper to the metal iron, and we want to look at our list. So if we find iron, iron's right here, and then we find copper, copper's down below. So in this scenario, iron is more reactive, which means iron does not want to exist by itself. So this reaction actually takes place. We will form iron 2 sulfate, and we will form copper. You could also form iron 3 sulfate. Doesn't really matter to me which one you pick to form in that case. I didn't give you any other info. But that reaction would work because iron is more reactive, and since it starts in the elemental form, it doesn't want to stay that way. It wants to be paired up with somebody. It would rather be in a compound. Okay, so that's how we use this activity series. So let's find another one. I'm just going to switch colors here. All right. So we've got nickel, and then we've got sodium chloride. So we're comparing the sodium and the nickel. So let's find nickel is right here. And sodium is right up near the top. So sodium is really reactive compared to nickel. So since sodium is already in a compound, it's not going to react, right? The higher it is on that activity series, it wants to be in a compound. So if it's already in a compound to start with, that's a scenario where we get no reaction. So we just write no reaction. Nothing would actually happen there. The nickel's just going to sit in that solution of sodium chloride and do nothing. Okay. All right, let's look at the next one. I'm going to go and change my color again. I'll go to purple. We've got lithium and we've got zinc carbonate. So we got to compare zinc and lithium. So lithium's way up near the top. Zinc is down below it. So lithium is the more reactive metal, which means lithium wants to be in a compound. And right now, when we start out, it's not, right? It's all by itself. So it wants to get into compound form. So that means a reaction takes place. We're going to get lithium carbonate form, and we'll produce solid zinc. All right, so that reaction actually takes place because that lithium, being so reactive, doesn't want to exist by itself. And then our last reaction, I'll go one other color. Let's go green. We've got aluminum and copper 2 chloride. So we're looking at comparing copper and aluminum. So we found copper, it's down here. And then we got to find aluminum, which is higher up. So aluminum is more reactive. Aluminum right now is all by itself. And remember, the more reactive things don't want to be by themselves. So if we're looking at this, we then have our reaction is going to take place. We're going to get aluminum forming a compound with chlorine. So we'll get aluminum chloride. And we will form copper solid. So this is how we use the activity series of metals to help us predict whether a reaction is going to take place or not. Okay. Very useful tool for determining if a single displacement reaction will occur. So at the back of your periodic table, you have an activity series of metals. There's also some info on the back of your periodic table that talks about the idea of if it's reactive with water or if it's reactive with an acid. So that information is there. A good one to check out and get comfortable using it. Okay, so let's keep going down. Here's a scenario where we have any metal above hydrogen in the activity series will displace hydrogen gas from an acid or water. Although sometimes heat must be applied to increase the reaction rate to the point where the reaction is noticeable. So we've got zinc and HCl. So if we look back here at our activity series, zinc is higher than hydrogen, right? Zinc is up here, hydrogen is right here, right? So zinc being more reactive than the hydrogen means that a reaction will take place. So we're going to get the zinc is going to react with the chlorine to form zinc chloride. And then we're going to produce hydrogen gas, H2. Okay, so that's a scenario because zinc is more reactive than that hydrogen in that activity series. Right? The zinc takes its place, it reacts with the chlorine to form its compound. Remember that the formulas for the compounds come from how those charges occur. So zinc was a 2 plus and Cl is a 1 minus. So when we crisscross, that's why we end up with 2 chlorines. Remember that elemental hydrogen has to exist as H2, right? It's one of those diatomic ones. All right, let's look at copper solid and hydrochloric acid. So copper is below hydrogen, right? So there's copper and there's hydrogen. So hydrogen is higher on that list than copper. That means hydrogen wants to stay in the compound. So this is going to be a scenario where we get no reaction occurring. Okay. And then the last one here is copper with water. Now, if you look at your activity series on the back of the periodic table, it's pretty clear. There's little markings on one column that will show you where it is things that are reactive with water. And copper is not reactive with water. You'll see that there's no little stars beside it. So this is going to have no reaction, which makes sense as to why we use copper in our pipes, right? If copper reacted with water, it would not be good to have our pipes in our house made of copper, right? So that's a good thing that it doesn't react in that case, right? So there's our scenarios dealing with water or an acid. So just take a look at the back of your periodic table. And then we've got a few more examples, right? Metal will displace the metal from a compound in a solution if the metal in the compound is located below it in the activity series. So if we look, this is just stuff we've done. So magnesium plus zinc iodide. So I'm going to go back to my thing. Magnesium is right here. And then zinc is right here. So magnesium's higher. Magnesium's more reactive. So if magnesium's more reactive, it doesn't want to exist by itself. So we're going to form magnesium iodide, and we're going to get zinc solid formed, right? So it's, again, these are just more examples of how we use this activity series. Next one's nickel compared to zinc, right? So if we look at that, nickel is actually below zinc, right? So there's nickel, and zinc is higher. So in this case, if zinc is higher, zinc wants to stay in the compound, right? So it's higher, it's staying in the compound. This would be a scenario where we have no reaction, right? So whenever there's no reaction, we just write no reaction. If you want to short form it, you could go no RXN if you want as a little short form, okay? But that's how we deal with it for metals. Now, there is also a single displacements that can happen where the non-metal switches places. We talked about this at the beginning of the video. So here is an activity series for some nonmetals, right? The most reactive is fluorine, and then sulfur in this list is our least reactive of the ones that we're going to deal with. So again, things that are most reactive, you're never going to find them free in nature on their own. If they're very reactive, they're going to end up as compounds. That's how they're going to be stable. They're not going to be stable in their elemental form. So when we look at this, we've got two scenarios. We've got fluorine, right? So we've got fluorine, F2. And we've got sodium bromide. So I want to look at bromine versus fluorine. So here's fluorine, here's bromine. Fluorine's higher, fluorine's more reactive, wants to be in a compound. But right now, it's all by itself. So it's not in the compound. So that means the reaction is going to take place. We're going to get sodium fluoride, and we're going to get bromine. And I'll balance this because the balancing was already started, the 2's there. So to balance it, we're going to need 2 sodium fluorides, and then it'll be a balanced reaction, right? But it's a similar idea. Now you're just comparing nonmetals, right? So in these reactions, we either compare the metals to the metals, or we compare the nonmetals to nonmetals, right? The only weird part is the hydrogen, because it can behave like reactivity-wise like metal does, right? Okay, the next example here is I2. I'm just going to switch back to my blue, this one, okay? So we've got I2, right? So iodine, and we have to compare it to bromine. So we've got bromine right here, and then we've got iodine, which is down below. So bromine is more reactive. The more reactive thing is already in the compound. That means no reaction, right? So that's how we deal with single displacement reactions. We can use the activity series to help us decide whether these reactions will take place or not. Okay, so that's the end of this video. Hope you enjoyed it and learned something. Watch the one on double displacement that's coming up next.